Hello. Hi, I'm Srinivasan. Today I'm presenting our vector commitment called Hyperproofs. It's the first vector commitment that is both aggregatable and maintainable. So this is a joint work with Alexander Trepanoi, Babis Papamantu, Alan Thomas Q, and Yupeng Zhang. We worked on this project when I was a PhD student at University of Maryland. Since then, I have graduated and moved on to Lagrange Labs, and some of my collaborators have moved on to other places as well. We love our Merkle tree, but there are times when you want to use something else. So this talk is about when they are when an alternative is useful and what properties do we have from that. So here is a quick primer. A vector commitment is a short commitment to an ordered sequence of values. It lets a prover compute a small proof of opening for an element in the vector. And any verifier can check if this proof is indeed correct by running the verify function. The key security property which we want from a vector commitment is called position binding. Say the prover has committed to some value m at position I, then the prover should not be able to come up with a different value m prime, a proof for m prime that is accepted by the verifier under the same commitment C. A good example of vector commitment is Merkle tree. And vector commitments are useful in verifiable storage, stateless blockchains, snarks, and many applications continue to emerge. So existing vector commitment landscape can be categorized into two broad categories. In the first category, we have schemes that are aggregatable, meaning if you have an individual proof, you can combine them into a single short proof. That's called as aggregation. And on the other hand, you have vector commitment schemes that are maintainable. So what I mean by that is whenever there's an update in the vector, you can update all proofs in sublinear time. The aggregatable vector commitment schemes have constant size proof. However, they are hard to maintain. On the other hand, maintainable vector commitments are, of course, they're easy to maintain, but you cannot efficiently aggregate them. So a good example of a maintainable vector commitment is a Merkle tree. Say that position 1 changes from value, say, from 5 to 10, then all the values all the way to the digest keeps changing. However, let's say I have a proof of inclusion proof for some value at position 7. I just have to update my proof wherein it intersects with the proof of 1. So that's what I mean by maintainability, and you should be able to do this in sublinear time. The quick way to do aggregation in something like a maintainable scheme like a Merkle tree is to snark. However, snarks in this context are not the appropriate tools. For example, it could take anywhere between 10 to 90 million constraints based on the choice of your hash function. And it could take anywhere between 20 to 83 minutes for a single-threaded code. And yeah, we do have more numbers on this. The long story short, snarks may not be the right tool to aggregate something like a Merkle tree. So the question which we ask in this work is, can we build a vector commitment scheme that is both efficiently aggregatable and maintainable? So why do we care about these two properties? First, the only other alternative we have is to using snarks, and they may not be the right tools. It's inefficient. And the other key reason why we want to use a vector commitment scheme with these two properties are in the context of stateless blockchains, where we need maintainability and efficient aggregation. Here is a quick summary of our results. So our vector commitment scheme is the first one to efficiently do aggregation and can maintain proofs. Since then, there are other works that also have these two properties simultaneously together. Our aggregation is 10x to 41x faster, and we can a single update say that there's a single update in the system. We can update all proofs in 2.6 milliseconds, and our proof sizes are small. It's log n, it's around 1.44 kibibytes, and yeah. However, all of this comes with a cost. Our aggregated proof size is slightly large. It's around 52 kibibytes. And we also need linear size trusted parameters, where linear is in the size of the vector. So a quick heads up, this has slight technical details. Even if you skip them, you should be able to follow the rest of the talk. So this is going to be the broad overview of the rest of the talk. First, I'm going to tell you how we commit to a vector, how do I compute a proof of opening, and then how do we maintain proofs in Hyperproofs. We also have schemes to aggregate proofs and other cool properties. However, I'm going to leave you, I'm going to ask you to look up the paper so that you have better context. So the fundamental building block which we use in our scheme is a polynomial commitment. So I'm sure here's a quick one slide, and I'm sure most of you know how it works. However, let's say that when a prover has a polynomial function f, and the prover wants to commit to it and compute a short commitment. Later, the prover wants to compute proofs of evaluation, let's say in this example at I evaluates to y. If I evaluates to y when you compute the function, the prover can compute a short proof, and any verifier can check if this evaluation proof is correct. So jumping into how we do commitments, say in this example, say we have a vector of size 8 from A0 to A7. What we do is we first build a function f. When you plug in the binary decomposition of I, say in this context I3, I2, and I1, and we get AI out of it. So this is a special polynomial which we build. So what we do, we first have a vector, and we encode it into some polynomial f. And that polynomial, when plugged in with the binary decomposition of the indices in the vector, gives out the value that is in the vector. So once we build this polynomial, so what we do is we use polynomial commitments to compute the commitment of the vector. We use something called as PST commitments. It's a multivariate version of KCG commitments. And even if you're not familiar with polynomial commitments, you can think of them as hash function with some cool properties, and you should still be able to follow the rest of the talk. But in this paper, we specifically use something called as PST commitments. So a proof of opening in this scheme is fairly straightforward. So once we have committed to the polynomial f, which is a multivariate polynomial. Oh, another key detail is the polynomial f has 3 variables. This is logarithmic in the size of the vector. So that's why in this example we have 8 elements in the vector. That's why we have a polynomial of 3 variables. Yeah, a proof of opening is just a simple evaluation proof. If we can evaluate f at these binary values, and if we get AI out of it, then we can use the PST evaluation proof as the proof of opening. Since the PST commitments have proof size log in the size of n, even our vector commitment proofs are log n, where n is the size of the vector. In this example, I have pi I, which is the proof of opening, has values pi sub 3, pi sub I3, pi sub I2, and pi sub I1. So once you let's say that if you want to compute a proof of opening for A0, and let that be pi 0, and pi 0 has 3 group elements. And let's say that you have the proof of A1, which has a bunch of group elements and so on, all the way for all the positions in the vector, and you have these group elements. So it turns out that due to the algebraic properties of our polynomial, the values that are highlighted in this chunk are actually, in fact, identical. So we can just replace them all into something called as, let's say, a group element A1. And when we go down a level below, the values in this chunk, this half of the chunk, have identical values. Let's call this to be B1, and the other chunk is also identical, and let this be B2. So we achieve these properties because of the way we construct the polynomial, and we can do this all the way to the bottommost level, and the values within these chunks are the same. So it's going to be C1, C2, C3, C4, and so on. So once we have these values, it turns out that these proofs form a tree where there is a specific relationship between the parent and the child. And we build this data structure, and we call this as multilinear tree. So this helps us in achieving a maintainability property of our vector commitment. So I'm going to redraw this tree in the next slide, and we call this to be multilinear tree. The leaves of this tree are the specific values in the vector, and all the way to the root are the group elements that constitute the proof of opening for each element, each value in the tree. So a proof of opening of phi will be like you have to traverse from the leaf all the way to the root, and that makes up the proof. So say if the position index phi changes by some value delta, then what we do is we can update this tree using some static information called update keys. And we use this update key, which is specific to an index, and the value delta, that's the value by which the leaf changed. And we can fix the we can update the proofs all the way to the top. So this works because of the way we build our polynomials, which I did not tell you how it works. I ask you to go look up our paper because you have more details on why this is true. But in essence, we have some static information called update keys that is specific to index in the vector, and we use this value to update the proofs along the way. So so you can see that by fixing the proof to the root, we can update all proofs, and the height of the tree is log n, where n is the size of the vector. It just takes log n time to update all proofs. I would love to explain more about how aggregation works. However, I'll defer the details to the paper. Here's a quick overview of the numbers we have, the benchmark numbers. So we can in our experiments, we can see that Hyperproofs is roughly 10x faster than a Merkle tree based on Poseidon. However, our verification is slower, and the proof size is slightly larger. However, in the context of macro benchmarks, when we do it, we have faster end-to-end performance than Merkle tree-based alternatives. So in conclusion, we have a vector commitment scheme that is efficiently aggregatable, maintainable, and something called unstealable. I didn't get to talk about unstealability. So this is a new novel property which we introduce in this work, where a prover can watermark the proofs they compute, and it incentivizes proof computation. And end-to-end performance is 10x to 41x faster than Merkle tree-based alternatives. And we can consider this to be an algebraic variant of the Merkle trees. Here is a link to our paper, and I'm happy to take questions if we have time.
Great presentation, thank you. Are there any use cases that you're excited about in the short term?
In the short term, I'm just saying as a theoretical object, but yeah, stateless blockchains is something which we can use, and other places where these two properties are useful is something, yeah, would be helpful, yeah.
Can the same technique be applied without needing a trusted setup?
That's a great question. I don't know how to do it, but yeah, we are actively looking into it, but I don't know how to do it.
Okay, and the aggregated proof size, is that, how does it grow with n or with the?
I'm blanking out on the asymptotics. I think it's log n. It uses ideas from inner product arguments. I'm blanking out on asymptotics right now, yeah.
Cool, thank you.
Do we have some other question? Nope. Okay, so thank you.